Hello, here we'll talk about application of orthogonalization to approximation problems. The official title is least squares approximation. Let's start with a typical example. Suppose that we have a collection of points which are scattered on the plane. And the problem is to guess a function which approximates this collection of points the best. What is the best and what functions we're allowed to have. So we have this data of a function that at value x1, say here we have, for the variable we have the function value y1 and up to the last in the least. And the easiest functions are linear functions, so that is least square linear approximation problem. We need to find a function, linear, hence this template, which fits the data the best way. So what is the best? If we draw this ideal function, the best would mean that the heights from points to the line will have to sum, so squares of those deviations will have to sum to a minimal possible value. So what we're minimizing is the sum of squares of all these vertical distances. And that is the least square linear approximation problem. So let's write the conditions we have for the template. The template has two unknowns, the two coefficients we are to find. And the data we have is this. So if we just plug the values for x in our template for the function and equate with the expected, we will have a system of many linear equations, or all are very easy just on two unknowns. And the more of equations we have, the less probability that we're going to have exact solutions. So we can write matrix form of that, and the matrix of the bulk of the system will have two columns. The first is just all one column, the second is the x values we have in our data list. Then the column of unknowns is just this short column of coefficients a and b, and then the margin on the right is with, again, the y coordinates of the data. So this system is most probably, if n is large and if points are scattered randomly more or less, this system is most probably unsolvable exactly. But what we are after is minimizing. So finding such solution, let me introduce short notations for the matrix A, for the vector of unknowns B, V, and the right hand side will be vector B. So we're minimizing the difference between the two. That's what this picture is representing. We want to find V with the minimal possible norm, the minimal possible length of this vector. So the such solution, if it exists, let's just call it V mean. That will be the minimal possible of all such length. So let's invoke geometry as a guardian for what is we are looking for. So we have a subspace of all vectors of the form a times something. So that is the image of the linear map given by the matrix A, or in planar terms, it's a column space of matrix A. because when we take a vector and multiply our matrix with it, we are just taking some linear combinations of columns. Like in here, we have two columns, and these are the coefficients. We take these columns with in a linear combination and then matching the right-hand side column. So we are we're having something unknown in this subspace, in the column space of A, and then we have our right-hand side vector B, which most probably is not in the column space of A, so the system is unsolvable, so it sticks out of the column space. And what will be the minimal distance from B to the space will be just the length of this perpendicular component of the decomposition of B, and the other component in this decomposition will be the projection of B onto the subspace, and that will be this difference, because the projection will be in this picture, it will be such which will minimize the length of the difference. The shortest length from the point to the subspace will be this perpendicular component, so that will be just nothing but A times V minimal. It will be nothing but this thing which is in the column space. And here we will have the difference of B and, or rather here, we will have the difference of B and A times V minimal. So that's how we can find a V minimal as the projection. But that involves many sort of steps in the computation, say finding the basis of column space, projecting down to it. Instead, we could just look at what the orthogonality, the condition that this vector is perpendicular to the space, what it gives us immediately. So let's just take it and use the fact that it is perpendicular to the column space of A. That means that scalar product of this vector with any of columns of A will be 0. And scalar product can be interpreted in terms of matrix multiplication. If we take the transpose of A and multiply with our vector, it has to be 0. So these are the two equivalent conditions, because being orthogonal to a subspace is being orthogonal to, say, all its vectors, but instead of all vectors, we can just take columns of A, because any other vector is a linear combination. And being orthogonal to any of the columns is the same as having this matrix product 0, because when we compute this matrix product, we compute effectively as matrix entries of the product, we compute scalar products of columns of A with this column vector. So that is the key to solving this minimization problem. We are not going to compute projection, we are just going to solve this system, and this system is called the least square system. This is least square system associated with the original unsolvable system. So if we just rewrite it, changing the sign for cosmetic purposes, we will have this equation. The relation between the original and this is just we take the transpose of the bulk matrix and multiply both sides with it. And then our minimizing solution for the vector V will be, for the vector of unknowns, will be just the solution of this equation. And what happens now is that this is solvable most of the time. In all the reasonable situations, this is solvable, well, solvable always, and even better, it has unique solution under very mild assumption. If we assume that the kernel of the linear map associated with A is 0, and that is the same as assuming that no vectors giving 0 when we multiply them with matrix A, then we could see that the kernel of this map is also 0. And it's simply because if we have a kernel vector in this map, it will have to be of 0, the vector in this kernel, say call it V again, or W. If we have this vector in the kernel, we could see that its scalar product with, so having it 0, it's equivalent to having the scalar product of A W with itself being 0. Because if we take this vector and we know that it is 0, we can compute the scalar product of it with just W. And these two scalar products are the same. And then this condition, we know by the properties of scalar products, guarantee that this vector is 0, so we'll have something in the kernel which is 0, which is almost empty. So that is now a condition for invertibility, because this matrix is square when we take a matrix, rectangular as this is, for example, and multiply with its transpose, we always get a square matrix. If we have 0 kernel, it's the same as to say that we don't have free variables. The matrix has to be all pivots in this Gauss elimination form, so it should be invertible. This matrix is invertible. And that means that this system has a unique solution. So under reasonable assumption, like this matrix is always satisfies this assumption, doesn't matter what x's are, unless, if they're all different, for example, if we are interested in reasonable set of data points where all x coordinates are different, then this matrix will satisfy this assumption, and then we will have always a unique solution, and that is the least square line. So let's finish or continue with an example where we're just looking at the least square line. Approximating, say, this given data. We just need to take this equation and turn it into its least square form by multiplying with the transpose away. So let's compute the product of A transpose and A. Transpose in this matrix, we will have matrix of size 2 by n, and multiplying with the original A. It's the same as computing scalar products. So this by that is the scalar square of all one vector, and it has the answer, which is the number of coordinates. This by that is the sum of coordinates of a vector, and the same here. The matrix we get when we multiply A with its transpose, it's always symmetric, so we don't need to compute that many entries. And the last entry, when we take the scalar product of x vector with itself, is the sum of squares of the coordinates, is the length of the vector. So that is the product of A transpose and A. This is a simple 2 by 2 matrix. A transpose times B is also a short vector of length 2 with 2 coordinates, and the first is the product of all one vector with y's, so that will be the sum of all y coordinates. The second coordinate of this short vector is the product of x's and y's, so that will be this quantity. And that's how a least square system will look like. On the left we'll have this 2 by 2, on the right we'll have this column vector. So let's imagine a set of 4 points I'll tabulate them. So choosing x values to be this and y values to be 1, 0, 3, 2, something like that. So the data will look like following: 1, 2, 3, 4. So at 0 we have 1, point at this y-axis. At 1 we have 0 value for y. At 2 we have 1, 2, 3. We have this value for y, and at 3 we have the value 2. So these are the 4 points we have to linearly approximate in the best least square way. Let's solve the corresponding least square system. The number of points is 4. Sum of x coordinates is 1 plus 2 plus 3 is 6. And the sum of squares of x coordinates is 1 plus 4 plus 9 is 14. On the right of the least square system, this product will have the sum of y's, which is 6 again, and the sum of x coordinates multiplied by y coordinates, 0 here, 0 here, 6 and 6. Twice 6 is 12. So that is the least square system for that data. And Gauss elimination is what we do. So halving the first row, we can make it look better. 2, 3, and 3 on the right. Not changing the last, keeping it as it is. For the elimination purposes, now we can do row 2 minus 3 times row 1. And we'll have 0 here, and then in this coordinate we will have 9 subtracted from 14, leaving us with 5, and on the right we'll have 12 without 9 again, and that will be 3. So now eliminating this entry above the pivot, I will do something like taking the first row in its place and scaling it up by 5. And then subtracting 3 copies of row 2 out of it. Row 2 is not changed. So scaling up by 5, I'll have 10, 15, 15. 10 will stay as it is. 15 without 3 times 5 is 0. 15 without 3 times 3 is going to be 6. And finally, that is the answer for A and B. 10A is 6, 5B is 3. So A is 6 over 10, which is the same as 3 over 5. And the same is for B. And that is the answer. And if we plot it, say, by 2 points, the value at 0 is 3/5. It's somewhere here. And then the value, say, at 3, it is going to be 9/5 plus 3/5. It's going to be 12/5. It's going to be slightly above 2. So the line is placed like that. And that is what the algebra is telling us. So we can really look at the values. This line function, this linear function, has at the data points at 0 it is 3 over 5. So let's call it L of x. 3 over 5 at 0. At 1 it is 6 over 5. At 2 it is 6, 9 over 5, and at 3, as we computed, it is 12 over 5. So we could compute the deviation, so the sum of squares of all these distances between the actual points and the line approximating them. That will be the sum of squares of the differences of these. So this deviation from the linear function will be 3 over 5 squared for the, rather the difference between 1 and 3 over 5 will be 2 over 5, sign ignored. Then the value at 0 is 6 over 5 all squared. Then the difference between 3, which is 15 over 5, and 9 over 5 is going to be 6 over 5. Again, ignoring the sign. And finally, this difference is 2 over 5. So what we have is 2 copies of 2 over 5 squared plus 2 copies of 6 over 5 squared. 25 is the square of the common denominator. And then we have 2 squared and 6 squared. So that is 40. 40 is 8 times 5, so we'll have 16 upstairs, and for cancelling 5 downstairs, we have this answer for the deviation. Why am I computing it? Is because the points, if we look at them again, the points are sort of spaced equally around the diagonal, and geometrically it sort of looks like diagonal is going to be a better fit for the set of data we have. The line is going to be, in sort of geometric naive measure, going to be closer to this point, the diagonal line, than the line we computed. But that is the sort of geometry is playing tricks with us, because it will be closer with respect to these sort of distances. And that is not what we are after. We are minimizing the discrepancies in the y coordinates only. So it is not geometric approximation. We can compute the total sort of deviation, quadratic deviation of the diagonal line from our set of data, and it will be 1 at every data point. So we'll have sum of 4 ones squared, but that is not going to change the answer, which is 4. And comparing this to that, this is slightly above 3, but way less than 4, which with this denominator will look like 20 or 5. So that is so much less. So this line is so much better. And again, algebra guarantees that this is the least square. The sum of squares of these deviations is the least possible for all the lines. So that is it for this video. More to come later.